Okay, so let's take a look at the notes from section 1.2. We started to do this in class and we didn't have a chance to get very far. So what we had said was that whenever we're factoring something of the form a cubed minus b cubed, that it is, a cubed minus b cubed, it's a minus b times a squared plus b, ab plus b squared. And so in our case, a is equal to x. Again, we're looking at the numerator here, and b is equal to 1. And so when we go to factor that numerator, we end up with x minus 1 times x squared plus x plus 1, all over our denominator of x minus 1. And we notice that these x minus 1s can cancel. And so really what it's saying is, other than at x equals 1, where the function is not defined, everywhere else it behaves like x squared plus x plus 1. So let's take a second to graph that. Again, we're really familiar with parabolas, so we would say, well, this is in standard form. So the very obvious thing I can plot is the y-intercept. So I'm going to come over here and plot that at 1. Then we can find the vertex. Again, hopefully you're remembering that to find the vertex in standard form, it's negative b over 2a, comma, f of negative b over 2a. So first we need to find that x coordinate. So it would be negative b, or the opposite of b, so that would be negative 1 over 2 times, and a is 1, so it's just negative 1/2. And then we'll plug that back in here to find the y coordinate. So we've got negative 1/2 squared plus negative 1/2 plus 1. In other words, 1/4 minus 1/2 plus 1. This gives us negative 1/4, and then plus 1 equals 3/4. So at negative 1/2, 3/4 is right about there. And if you remember, the axis of symmetry is going to go right through that vertex point, and then it's going to be a mirror image on each side. So then I also know that at negative 1, it's also 1, just because we've got that symmetry right there. And I'm just going to plug in a couple other points to see where they end up on the graph. So if I plug in positive 1 to this, again, I'm going to be careful because I can't actually achieve that value, so I'm going to put a hollow dot there. If I put in 1, 1 squared is 1, plus 1 is 2, plus 1 is 3. So I can't actually achieve that value, so I'm going to put a hollow dot right there. I am allowed to plug in negative 2, its mirror image, so there will be a solid dot there. And then let's do the value for 2. If I plug in 2 there, I get 4, plus another 2 is 6, plus 1 more is 7. So up here at 2, 7, and then its mirror image here at negative 3, 7. Again, as I get to that point at 1, 3, I know that's what the function hopes to be, but it can't achieve that. Okay, so there is our graph. And so what it's going to ask us to do here is say, well, let's just confirm from a numerical perspective that what is happening in the graph here is that we can see that happening here in our numerical table. And so what we're doing is that point that's in question, since we're not allowed to choose x equals 1, what does that look like? As we're approaching it, we're getting closer and closer to it from values below it, or from the left. What are those values approaching, to see what would we think that the value of 1 should be. And then we do the same thing, but from the opposite direction. Let's choose values that are higher than 1 and see, as we approach 1 from now the right, what is the value that we achieve, right? So we're going to say, we're going to look at x approaches 1 from the left. All right, so from this direction, what happens? And then x is approaching 1 from the right. And we want to know what happens then. our hope is that they're going to match, and so we'll have an idea of what should happen at 1. All right, so you're going to need your calculator for this. We've also had some stuff in there already stored, and so we need to make sure that we are not getting any interference by our stat plot or anything like that. So just if you would go in to stat plot, and any plots that are on, I would suggest that you turn them off. And again, you do that by hitting enter and then moving your cursor over so that off is highlighted, and then press enter so that removes it from on, and now it's off. All right, to get out of that screen, the other place that you might have stuff saved that will interfere with this process is in your y equals. So just anything that's in there, you can just get rid of. All right, so then we're going to enter not this function that we're using, that we use to help graph, but this function right here. So as you go in, make sure that you put parentheses around this for the numerator and the denominator so that the calculator gives you the correct values. All right, so we've got x cubed minus 1 divided by x minus 1. And again, because our stat plot was on, because we had other equations in there, our graph might not show up where we want it to. And so we need to make sure that we are consistent with where we know the graph is going to be. So again, go into your window. I just set mine up already, but I have mine because my graph goes -7 to +7 on the x. I set my x min to be -7 and the x max to be +7. And then you would do the same thing for the y-axis. Again, it also goes from a minimum of -7 to a maximum of +7. You could just note, hey, there's nothing going on down here. I'm just not going to do that. I'm going to change my y-min to 0. That's totally fine too. And then you would just end up with mostly only just seeing that part right there. Okay, so then we graph. And we see it does look very much like what we graphed right here. Again, if you want to take a minute and pause this video and just zoom in around that point where there's the hollow dot, you should see a little bit of a blip right there. That it won't, you know, it's not perceptible by your eye right now, or perceivable by your eye, but as you zoom in, you should see not a hollow dot, but just a jump from that point. So if you want to explore that, please pause and come back. All right, so what we're going to do now is we're going to use the value function on the calculator to figure out what is the value of the function at 0.75. So we're going to go back, second trace, and then value is our first one, and hit enter. And we're going to say 0.75. And so that is 2.3125. All right, I'll do it for a couple more, and then I'm going to ask you to pause the video and finish doing that on your own. Second calc, value, 0.9. I get 2.71. Let's do it one more time. Second calc, enter, 0.99, 2.9701. All right, so pause for just a second and come back. Again, don't try and do anything with 1. You could, but actually that would be a great idea. Try and see what happens with 1 and what happens with the y, and then we can talk about that in just a second. Okay, so hopefully you got the values for 0.999. You get 2.997. For 1.01, it should be 3.003, then 3.030, then 3.310, and 3.813. Excuse me. And then when you try 1, here's what you should have found. It just doesn't give you anything. All right, it doesn't know what to do because it can't, there is no y value associated with that. All right, so we're still wondering, we can't plug it in directly because it's also going to give us something there. That just doesn't make sense. All right, so we say as x is moving closer to 1. So again, we saw that x is moving closer to 1. Then what is f of x doing? All right, so we've seen that we're moving closer to 1 from the left, or values lower than it, from the right, from values higher than it. But the question now is, what is f of x doing? So as we move in from the left side, values lower than it, we start to see that that value is increasing, increasing, increasing. In fact, increasing significantly close to the value of 3. All right, we see the same thing here. As we come in from the right, values higher, x values higher than 1, we see the y value now decreasing. 3.8, 3.3, 3.0, 3.003. But again, what it is doing is the same thing that it's doing as we come in from the left, and that is it is approaching 3. All right, it's getting closer and closer to 3. And again, that's what we saw here when we canceled out that factor that was causing the problem and said, hey, everywhere it should behave like this except at 1 where we know it can't exist. And hence that's where that hollow dot came from. All right, so here f of x is approaching 3. And again, from this direction, same thing, f of x approaches 3. And if you're wondering why I'm making a big deal about both sides, we're going to see in just a minute examples where that is not true, that it does different things on each side as it approaches that target value. And so it's important for us to say that it happens on both sides. So we say what this process is that we just did is this limit process we've been referring to. So we would say the limit, all right, again, that moving incrementally closer and closer and closer to our target value, so that we're calling a limit. The limit of the function f of x as x is moving towards 1. All right, so the limit of the function as x is moving towards 1 is 3. All right, so this part right here is telling us what the value of the function is, and this is telling us what x is doing in order to get us there. Right? And this, the way we read it, because again, you look at that and you'd be like, how do I even pronounce that? We would say the limit of f of x as x approaches 1 is 3. All right, the limit of f of x as x is approaching 1 is equal to 3. All right, so this was what we would write for this specific problem, this specific function approaching this specific point. In general, it's saying if some function f becomes arbitrarily close to a single number L, right? L is going to be our limit. That's essentially this number right here. As x is approaching some number c, in our example that was 1, from either side, again, I said that we'll see in just a second how it could vary depending on which side you're coming from. So we want to be consistent. That is saying it doesn't matter which side we come from, it's the same thing. All right, so as f of x becomes arbitrarily close to some number, so the y value, the function, becomes close to some number, as x on the x-axis is approaching some other number, then the limit of f as x approaches c is L, and we write this as the limit of f of x as x approaches c. Again, in our specific example, it was 1, but in general, we're just going to call that value on the x-axis c, is equal to L. All right, sorry, my underlines are making that look weird. All right, so the limit is equal to L, and again, now a problem, that was a 3. Okay, let's do another one. Now that we have the idea of what this process is, we're not going to be able to cancel this one out like we did, so we're going to have to do a little bit more work for our graphing, but we will look at that one. Okay, so let's enter that into our calculator now. So go ahead back in, and you can clear the function that was in y1 already, since we're done with that. And we're going to put that in. Again, I would Make sure you put parentheses around the bottom as you type that in, just so that you're sure that there are no problems there. So I'm going to do x divided by parentheses square root of x plus 1. I'm going to end that parentheses to say that that's the end of the square root. Again, depending on which type of calculator, you might just have to move your side arrow over to get out from underneath the radical. All right, and then minus 1, and then end my parentheses for the denominator. The grid that we have is the same one that we used up top, so your x min, x max, y min, y max should still be the same. All right, now let's take a look at the graph here really quickly. All right, so maybe you recognize that the pattern of a square root function, which if we rationalize this, we could end up having it look more square rootish. All right, but let's just go in and plug in a couple values here. So the smallest we could go, again, remember in our conversations about domain, we have to be concerned about two things. One is we don't want to get a negative under the radical. So we would say, okay, where is x plus 1 equal to 0? That's the lowest we can go. So if I solve, I get x equals negative 1. So the first value I'm going to plug in to this is negative 1 to see what happens. So if I plug in negative 1 up top, I've got negative 1. And in the denominator, negative 1 plus 1 is 0. So that part drops out. And then all I have in the denominator is negative 1. So at negative 1, I end up getting a value of 1. So right there. I can't do 0. Again, it's telling me, well, we could see that it's not 0 because if we just blindly tried to plug it in, we would get 0 plus 1 is 1, square root of 1 is 1, minus 1 gives us 0 in the denominator, and so it's going to be undefined there. Again, we'll talk about other techniques that we could use, kind of like how we fixed this a little bit so that we could at least look at the graph. We will do other techniques like that, but not right now. So for right now, we're just going to leave that blank. All right, when x is 1, we end up, actually, I'm going to put in 3. That'll make our lives a little bit easier. If I put in 3 here, 3 plus 1 is 4. Square root of 4 is 2. And then minus that 1. And then up top, I had put in 3. So I end up getting 3 over 1 is 3. So at 3, it's also 3. All right, and I know from my curve that it is very square rootish looking, so I'm going to go like this. Again, we'll come back and we'll adjust that 0 value. Right now it's looking like it's about 2, but this is really going to tell us what's going on. So we'll see more closely what that actually looks like. All right, so we're going to go in and we're going to just fill these in by doing the calc, the second calc. So I'll do the first one with you, and then I'm going to ask you to pause and do the rest on your own. All right, so we put in negative 0.01, and we get 1.99, let's go 5, all right? So you go ahead and you fill these in. Again, you're going to try and do 0, and it probably is going to give you the same thing it did when we did it up above, which is it's just not going to give you a y value for it. So go ahead and fill those in and come back when you're done. All right, so you should have gotten 1.999050 and then 1.99995. Over here, I got 2.00005. This one I got 2.00005, and then 2.00499. Right, and so we would say, okay, what's going on here? As x is approaching 0 from the left, or from values that are smaller than 0, what's happening? Well, we can see that we're getting closer and closer and closer to 2, right? And we check again from the other side as we approach values, as we approach 0 from values greater than 0. So all our values here are positive because they're greater than 0. We just keep getting closer and closer and closer to 2. So we would say the limit of f of x as x approaches 0 is 2. Again, what is happening with the function based on what is happening with the x values? All right, so here it's saying that the y values are getting closer to 2 as the x values are getting closer to 0. Right, so we can go back in here and adjust this a little more and say, hey, this is actually what's going on right here. That is a hollow dot, but otherwise this is going to go on something like this. Okay, gosh, I'm so bad at making sure I move up my paper when I do that, so hopefully that part didn't get cut off. I just added a hollow dot there instead of just having it go through. Okay, let's take a look at the next page here. And it's asking us to find the limit of f of x as x approaches 2. And the function f is a piecewise function. It's defined very simply. It's saying that if x is 2, the value of the function should be 0. Anywhere else, it should be equal to 1. All right, so if we think about what does this look like, this is something our calculator is not going to be very helpful with. And so we would just say, all right, at 2, I want the function to be equal to 0. All right, so check, I've used that part. Everywhere else, anywhere where x is not equal to 2, it wants it to be 1. Right, so for example, at 3, it wants to be 1. At 4, it wants to be 1. At 5, and at 6, and at 7, and everywhere in between, including 2.0001. All right, all of these values, it wants to be 1. All right, same thing in the opposite direction. At -6, it wants to be 1. At -5, at -4, we keep going. All the interim values, all not imaginary, irrational, non-integer values between these coordinates, it also wants to be 1. Even up to 1.999, it still wants to be 1. Right, so what we're going to have is a hollow dot right here on this line, because the value that it assumes is 2. And I'm sorry, at 2 is 0, and so therefore it's not actually defined there on this part, but it is defined right here. It's defined to be 0. All right, so the limit of f of x as x approaches 2 is not the value that it's actually taken. The limit is saying, what is the function doing as it's approaching 2? All right, so as x is approaching 2, the y values are approaching 1. Same thing from here. As x is approaching 2, but now from values less than 2, what is y doing? Y is still staying along this course of being 1, right? So the function is approaching 1 even though at that point it's defined to be 0, right? So I would equate this something to like peer pressure, all right? It's like, you know, what do all my friends say I should do? You should come to the movies with me. You should come to the movies with me. You should come to the movies with me. You should come to the movies. Same thing over here. Everybody externally is telling you you should do something. Sometimes you'll agree and then your value will be right there. And other times you're like, nah, I just want to sit home and read a book. Or, you know, do something else. So it's the limit is talking about what does all the evidence around me say I should be, regardless of whether I agree at that one spot or not. All right, so even though everything about this says you want to be 1 at 2, 2 says no, I'm going to opt out and I'm going to choose to be 0 at that point. Right, so again, we're not looking, when we talk about the limit, we're not talking about what is exactly happening at that point, but what does all the evidence say around it. All right, so we have actually talked about 2 of the methods for finding limits so far. One is the numerical approach. That's what we just did back here, where we filled in this table and we said, hey, what is going on? What can I see from this table? All right, I choose values on the left approaching that value and from the right approaching that value, and I want to see, do they match at some point? All right, so that's numerical. That was the first one. Graphical, again, we've done that side by side with it. We've said, what does it look like on the graph? All right, what does it look like on the graph down here? What does it look like on the graph? So we've done both of those. The third one, which we're going to look at in the next section, not in section 1.2, is the analytical approach. And again, we kind of have to suffer through with this method that takes a long time because historically that's the way it developed. And so as we approach this the way it was approached, thousands of years ago or hundreds of years ago, that we would do it the same way. And so our analytical approach is going to come last, and that again is going to be in the next section. So now that we've seen these two and we know to anticipate this, we still have maybe this lingering question of, well, is there ever a time that a limit is not going to exist? And the answer to that question is yes. And there are 3 times when that will happen. So we're going to look at examples of 2 of them, and then I'm going to ask you to go look at a 3rd in the book. It's just very difficult to draw, and so it's easier for you to just look at it in the book. All right, so the first way that a limit would fail to exist is if the graph looks different as we come in from the left and the right. So again, we've seen 3 examples where as we approach something from this direction, the graph is doing one thing. As we approach it from another, it does something that leads it to the same point right here. All right, so doesn't matter which direction we come from, all the evidence points to this being the limit. So are there situations where we might end up with, as we come in from the left, it looks like this, and as we come in from the right, it looks like this. And there is disagreement about the value that it should be. And so that's what our first example is going to look like. So this is a classic example. We're going to see it a lot throughout the year, and each time I'm going to remind you of what to do because for some reason this just doesn't naturally stick in your brain. So we need to find out what is happening as we approach 0 from the left and what is happening to the function as we approach 0 from the right. All right, so again, because our cutoff is 0, when we say values left of 0 or less than 0, we're always talking about negative values. So one of our categories will be what happens when x is less than 0. And the other is going to be for values right of 0 or for values greater than 0. Well, in that case, because it's 0, it just means anything that is positive. Okay, so then let's take a look specifically at the absolute value of a number. So in a case where x is greater than 0, so let's say 5, when we take the absolute value of 5, we get 5 back. When we take the absolute value of 17, we get 17 back. When we take the absolute value of 1/2, we get 1/2 right back. So whenever x is greater than 0, absolute value does absolutely nothing. All right, it preserves the value of the number that you put in there. So for our function f of x, we're going to say that the absolute value of x over x, when we're talking about values of x greater than 0, is exactly the same as x over x, because for values greater than 0, absolute value does nothing. It preserves the value of the x. Right? So anywhere where we are x greater than 1, this function is x greater than 0, this function is equivalent to 1. All right, so we can plot some points there and see what that looks like. So for 5, let's say absolute value of 5 over 5 is just 1. Absolute value of 1/2 over 1/2, that's also just 1. All right, absolute value of 3 over 3 is just 1. All of these values are 1. Right, and I'm going to get arbitrarily close to 0 because that's where things are bad, because then I get 0 over 0. All right, so let's talk about what happens when x is less than 0. Well, if I take absolute value of -5, it becomes +5. If I take absolute value of -17, it becomes +17. When I take absolute value of -1/2, it becomes +1/2. So what's happening? Well, it's changing the number inside to its opposite, right? To its additive inverse. And so it's taking, and essentially we could think of it as multiplying by -1. All right, so if I took -5 and multiplied it by -1, I'd get +5. -17 times -1 gives me +17. So when we're looking at values less than 0, absolute value of x over x, again, what this is doing is it's taking the value that we put in and multiplying it by the opposite, or multiplying it by -1. right? And then this x value, nothing's really happening with that. So then we would say, okay, well, negative x over x, that's the same thing as negative 1. Right? Again, the values are identical. The only difference is that negative sign. And so when it reduces, it's going to become negative 1. Right? So if we did the same thing over here, if we said, well, absolute value of negative 5 is positive 5, divided by negative 5 gives me negative 1. Right? Absolute value of negative 3 is positive 3, divided by negative 3 gives me negative 1. And it's going to keep doing that, right, until we get close to, but not touching 0. And again, we can't define what 0 is, right? It's 0 over 0. And so at this point, we're going to put a hollow dot because it doesn't exist at 0. And we'll put a hollow dot here because it doesn't exist as we get to 0. Right, and so what we would say is, hey, look at this. As we come in from the right, it approaches positive 1, but as we come in from the left, it approaches negative 1. There is no agreement, right? So we would say in this case that the limit does not exist. All right. Or we could say up here, more formally, we could say does not exist. And because sometimes we get lazy, we would just write D and E, does not exist. Okay, let's talk about one more. So discuss the existence of the limit of 1 over x squared as x approaches 0. And so hopefully you remember that the graph of 1 over x looks something like this. All right, the squaring the x part is just going to end up flipping this part up. All right, so our 1 over x squared is going to, it will change the shape of this a bit, but the most significant thing is that this negative part is going to end up becoming positive because we won't be able to get any negative values out of this. All right, so let's just plot a couple points. When x is 1, y is 1. When x is 2, y is 1/4. When x is a half, 1 over 1/2 squared, that would be 1 over 1/4, which would be 4. Right, and then we would get exactly the same values on the other side. Right, so it's going to look like this. Sorry, I don't know if you can actually see this right now, but let me finish drawing and I'll scooch my paper up. Okay, so it should look like that. All right, so discuss the existence of the limit of the function 1 over x squared right here as x is approaching 0. All right, and so what we see is, let's start from values less than 0, so negative x value. So as we approach 0 from the left, what is the function doing? Well, the function is going up and up and up. And as we keep getting closer to 0, this is going to continue to grow in an unbounded manner. Right? And so there is no finite number that we can say, oh, it's approaching 47 or something like that. It's going to continue to grow in an unbounded manner. Same as we come in from the right here, our values greater than 0. It starts out very low and then it starts to grow and then it grows very quickly and it's not going to stop. So it is going to approach positive infinity, but we would say since it is unbounded, we would say that the limit doesn't exist. So for this one, we would say, sorry, I need to make sure I say this correctly. We would say because, wow, I can't even read that. Because f of x is not approaching a finite number L,